I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics. And this video is going to overview Physical Chemistry for the Life Sciences, edition number 2, chapter 2 in this textbook. And as far as general information about physical chemistry for the life sciences or biophysical chemistry, I have a website that I keep with general information on all topics in this area. You can also reach me at this email address if you need to reach me directly. So the first part of Atkins' book, the second edition, goes through biochemical thermodynamics, which is our macroscopic theory for understanding biochemistry and biochemical processes. So we've made a different video looking at chapter 1, which is the first law of thermodynamics. And today we're really going to be looking at the second law of thermodynamics. And this is really what I would say is at the heart of thermodynamics, and the first two laws really define what we mean by the conservation of energy being the first law, incredibly fundamentally important. And it is something we kind of already have an intuition of from numerous other scientific fields, et cetera. It comes to play a lot. Now, in the second law is where we're going to introduce entropy. And this is really what I would say the crux of thermodynamics, chemical or biochemical thermodynamics, is really understanding entropy in its relationship at both a macroscopic level and a microscopic level to really get an understanding for the theory of thermodynamics that we use to understand biochemical processes. So, like I've done before, this is not meant to supplement reading the textbook chapter, going through the example problems, working things, looking at some of the checklist of the key concepts, discussion questions to make sure you understand some of the concepts being discussed, the excellent set of exercises and projects associated with this chapter is really how you're going to, understand this material the best. This video is really meant to just kind of overview the topics covered in this chapter on this important topic of the second law of thermodynamics. And what I like to do is just basically provide one slide on each of the major subtopics that this book covers and are listed here. And it's really breaking into what I first mentioned, which is the second law and its introduction and understanding of entropy. And then, because of the huge importance of the Gibbs free energy in chemistry and biochemistry, the second part of this chapter, after we're now able to introduce what entropy is and something about heat that allows us to look at kind of this heat work relationship that we use to define chemical work in the Gibbs free energy, which we'll get to. So the first is looking at kind of introducing, before we actually introduce the second law and what entropy is, et cetera, it introduces some macroscopic concepts that we're very familiar with. So it's basically helping us define what is kind of in a spontaneous or a natural direction as a function of time that we're used to seeing. And it points out some things that we have a lot of intuition for. Like, for example, if I told you kind of a thought experiment, like take, within, say, a container, all of the molecules in that container and say, put them up into one, small volume. Say, for example, we compress some CO2 gas into a small little cylinder, and it's at, higher pressure and at room temperature. And then I said, now relax that condition and let it expand into a larger volume container, for example. So we would have all the molecules, say, in one area, and then we allow it to expand into a larger volume. Or we just say, like, we make an initial condition where even though it was in a larger volume, we put all of the molecules kind of in one area. And we ask what would happen as a function of letting that constraint go, whatever was holding those there, or whatever created that initial condition, what would happen? And we have an intuition what would happen. Like, gas molecules, and same with liquid, they spread out to fill their container. right? But you don't typically, and that would happen if we made this initial condition, it would spontaneously do that, right? But the reverse doesn't happen. So there's in a sense, an arrow or a direction that has an intuition to it. But what we don't see is the reverse happen ever, from intuition, which is you have gas, like in this room, we have gas molecules throughout this room. There's a chance. Why don't they ever all come together in one area, right? Like shown here. So this kind of going back in this direction is not spontaneous, right? And so this is showing matter of specific, in kind of 2D of a kind of a specific like number of particles. We can kind of think of the same with, something a little more vague like energy, or something that isn't particles directly, but like energy. We could have a hot spot in an area indicated by red, and then it gets colder in this direction, right? So we have a temperature gradient in some samples. Say we've heated this up real quickly. And what happens over time? What happens is spontaneously, just over the course of time, that temperature distributes across that, via its thermal conductivity, etc. But what we don't see is the reverse. If we have kind of heat distribute evenly, energy distributed evenly across, say, a metal cylinder, we don't all of a sudden see part of it get really hot and the other part get colder. Even though that could conserve energy, that's not what happens in real physical processes. And so the second law helps us understand this direction, and they'll call it a lot of things, a direction in time. It gives it time's arrow. But why things happen in a certain direction and not, in the other direction. So the book starts by setting up what some of these spontaneous natural changes are, and so that we kind of have an intuition for them. And what the second law says is that for things to happen spontaneously, in that is to increase its entropy. And so what we're going to end up spending a lot of time doing is trying to really understand what entropy is from several different angles, from a microscopic perspective, from kind of a heat engine macroscopic, what is it as related to heat that we have some intuition for, a macroscopic behavior. You can also look at it from fields that you wouldn't naturally think are directly related, like from information theory and Shannon entropy, how information directly relates to entropy. And this is why you often hear it in computer science, and especially in cryptography and everything. What was the entropy of that, et cetera? It has a direct relation to the macroscopic entropy we're talking about here. The second law of thermodynamics has far-reaching implications through all of fundamental physics and all scientific fields that use those fundamental theories. So Rudolf Clausius, who is one of the really pioneers of thermodynamics, specifically entropy, is famous for making one of the general statements about the second law of thermodynamics, which is the entropy of the universe tends to a maximum. I tend to like to put that in a very specific mathematical formula, math being the language we use to describe any science. So, which is the change in entropy with respect to time, right, is always going to be greater than or equal to 0, right? And so this is often mathematically how we would state the second law of thermodynamics, and this is how it's often put into words. Now, one of the complications, the first law, conservation of energy, it's almost succinctly put in one statement that you can, and then it's just how we conserve that energy and how we break it up to look at it in useful, meaningful ways for specific problems. And in macroscopic thermodynamic systems, especially biochemical systems, et cetera, it typically makes sense to split it up into work and heat and to say that those things are conserved, or the overall energy of an isolated system, like the universe, as far as we understand, is conserved. Now, the second law, while it can be stated as I've stated it here with Clausius, has lots of different basically fundamental statements that have been given to it. So this being one of them, a lot of times they'll put, they'll first say of an isolated system, that the entropy of an isolated system must always either stay the same or increase, as I've stated here. Some people will talk about it as with respect to engines and cycles, that in any cycle, in any closed cycle system, that you either have to, entropy either has to stay the same or increase, etc. So there's several different ways that the second law have been stated, both in words and mathematically. So I like to show another, which is one of the other most common general ways to write the second law, is to introduce entropy in kind of almost a definition way, which is to say that the change in entropy is either equal to or greater than the change in the heat over temperature. And oftentimes, as we've discussed before, this delta, sometimes this infinitesimal change, which is also indicated by this derivative here, this is indicating that it's a path dependent, while this will be a state function that will end up being path independent. But this is really a change, and oftentimes sometimes this gets left out, the change. And we've talked about this before. This can often be common, like when we say, the height of something, like, the height of that mountain is 10,000 meters. What we really mean is it's a delta H, right? It's delta, it's with respect to sea level being 0, right? So a lot of things that we indicate in science are really changes in a variable. It's rarely absolute, but oftentimes we're so common to drop that. We just call it the height. We don't call it the change in distance or the change in height of something, right? We just say it's the height of something, or the altitude. But it's really a change in something. And the same happens here. So often that gets dropped. And what your book does is go specifically into a special case of this. The special case where this isn't an inequality, but an equality. And it's an equality that the change in entropy is equal to the heat over the temperature, the change in heat over the temperature, in a reversible process. And it goes on to really try to describe, because you can really separate the second law and thermodynamics into reversible thermodynamics and irreversible thermodynamics by whether the entropy is equal to this quantity or greater than. And if it's greater than, irreversible processes, which can be spontaneous, right? But you can also do these in such a way, experimentally, et cetera, that you keep them reversible. And it usually means kind of small incremental changes. In something like you're very familiar with introductory physics, this is when we talk about frictionless things, et cetera. We do things slow enough that we don't dissipate our work into heat, et cetera. So this is kind of how your book defines the second law. And again, is a very common way to throw the restriction of that we're going to really look at entropy in a reversible sense. And one of the reasons your book does this, instead of starting with the kind of these inequalities in a more general sense, is really when we're doing introductory thermodynamics, and almost everything we're going to cover in this course is all reversible equilibrium thermodynamics. There's a whole separate advanced topic on irreversible non-equilibrium thermodynamics, which I would say is often not covered much at the undergraduate chemistry, biochemistry level. It's typically reserved for more graduate level courses. But I think it's important to recognize, and especially in biology, where irreversible and non-equilibrium processes are very important for life itself. So it's important to realize that. And then, the book has several figures. I show one here, just kind of showing some of the, the change in entropy with respect to, for example, a ratio of temperature here, that you're increasing this entropy as a function of temperature, et cetera. So then there's really the first two laws of thermodynamics are the pillars that we build it upon. The zeroth law and the third law, which often help define an absolute temperature scale and what we mean by an absolute entropy. comes because of this statement, that the entropy of a system approaches a constant value as the temperature approaches absolute zero, which is helped define. So that's why we use a Kelvin scale, which is an absolute temperature scale, from absolute zero being 0 Kelvin up in temperature to say, 298, which is around room temperature, et cetera. It's an absolute temperature scale, and it's typically what we use in the physical and chemical sciences. And because it's always approaching, in other words, it's dispersionless as you get near absolute zero, it stops changing, it comes in horizontally here, that we can always kind of define that at absolute zero as being zero entropy, because your delta S is basically approaching zero in the limit as T goes to absolute zero. And so your book kind of shows how we typically renormalize everything and call this, the zero, it's our defined, in a sense, standard, zero of entropy. And that now allows us to often write absolute entropies, where we're always referring everything back to 0 degrees, absolute zero being what we define as the zero of entropy in the system. And then how we take entropies and how we look at those with respect to derivative properties or changes in entropy, like heat capacity, et cetera. Because we looked at heat capacity in chapter 1 as its relation to enthalpy. Now we'll see that it's directly related to entropy as well. And then after kind of introducing what I would call that classical definitions of thermodynamics, it's through engine cycles like Carnot cycles, where you have isothermal and adiabatic processes, which we covered in chapter 1, or define isothermal constant temperature, adiabatic. Now we'll say that as being constant entropy or constant heat in a system. Your book also, because this is for more chemistry, biochemistry type audiences, really takes some time to also show how entropy is related from a molecular standpoint. Now this can be put in much more rigorous terms after you've had some microscopic theoretical understanding, quantum chemistry, quantum biochemical systems, spectroscopy, et cetera, where we can really define these number of microstates or a number of configurations in a system. And so we'll give a general sense for them now, but really when you come back to this in statistical mechanics, et cetera, is when you can, you've had some of the microscopic understanding of what these microstates are. And so the log of those, specifically the natural log, so written it here, is in a sense the log of the number of configurations times a constant, which we often call Boltzmann's constant. Now we often give it a sub B, is the entropy as well. And like I said, this is just, and we can look at this as, so the book also kind of gives an explanation of entropy from a molecular standpoint and talks about, for example, the number of different configurations of how you can put hydrogen around oxygen in an ice crystal, and shows the 6 different configurations, and talks about configurational entropy. It talks about if you, for example, make in a 2-dimensional sense the volume bigger by making this length longer, that you can see that if you were at a specific temperature here, that would, now you would have more configurations, because if you looked at, for example, particle in a box, you would have more energy levels available to you, all within a certain temperature range. So you would have more microstates. So this W would go up in this sense, which means entropy would go up in this sense as well. And then I like to just remind that this is all because of the pioneering work of Ludwig Boltzmann, who even, this is such an important way of looking at entropy, especially from the molecular sciences standpoint, that it was, written on his tombstone as his real crowning insight, into the fundamental nature of of thermodynamics. And really, it can't be overexpressed. I mean, this is really the gateway into our connection between the macroscopic theory of thermodynamics and our microscopic understanding in quantum mechanics, et cetera. And the bridge being, the Boltzmann equation and the statistical mechanics or statistical probabilities that go into large numbers. So then the book reminds us of things we've seen at kind of introductory chemistry level, that we can now start to look at the change in things, and this is a state variable. So, which means it's an exact differential. So it's path independent. And so that we can look at it kind of the same way we did the enthalpy, which we introduced when we were looking at the first law. And one thing you might ask is, why aren't these, delta S's? Because before we would often do this as the delta S of, say, formation. And this is meant to indicate that it's a standard state. So we're still at the standard state. The M is for molar, which is fine. So we're going to do it per mole. We're going to turn those extensive variables of entropy into molar entropies to make them intensive. So we can understand that variable. But why doesn't it have a delta here? These are in absolute entropy terms because of the third law, that we can always state that we're going to reference this back to absolute zero, or our reference state for everything is the same. Zero entropy at 0 degrees, absolute zero temperature in Kelvin. So that's what allows us to kind of drop these delta S's. But these really are the change over that. It's just that we have a standard state that's the same for everything that allows us to do these. So these are molar standard state entropies, and it's by its stoichiometric coefficient, and we sum up all the products, and we can do this versus the reactants. And so Hess's law kind of works the same here. And like I said, we can say that this change in entropy, that after we integrate it, we would say is a delta S like this, is a state variable and is independent. So it works like the enthalpy did. It works like the internal energy did, et cetera, where the change across it, we can take whatever path is most convenient for a problem, the one where we can know the variables, and that it would be the same if we took a different path. Okay, and we cover the book covers chemical reactions because of its importance in what we're dealing with here, which is in physical chemistry, where we really often are looking at chemical changes of a system. So that gives a brief introduction to entropy, both from kind of a molecular standpoint, from a macroscopic standpoint, and kind of more or less reminding us of things we saw in our introductory chemistry classes. Maybe just looking at it a little more rigorously, putting it in kind of calculus or change mathematical terms, et cetera. And so because of the importance of how often, now that we understand this type of heat, that heat now is really, in a reversible sense, related to temperature, that the heat in a system is related to the temperature, the change in entropy of a system. So now we really, and we can start to really quantify this term. We already had a sense for what temperature is, and now it's giving us a sense for this disorder, this entropy, this ability, these microscopic configurations, this relation to probability and in information theory, et cetera. We come back and we want to now look at, just like with enthalpy, instead of looking at internal energy directly, we looked at a different type of energy that we called enthalpy. And the reason we did it is because we're often at constant pressure, where the enthalpy is directly related to just the heat in a system. And that gave us, by looking at it, energy in that dependent variables, kind of allowed us to make some direct relation to heat. Now we'll be able to look at heat in this way. And what we want to look at is energy as it's related to chemistry, the change in chemical processes under what I would say are the typical variables in either biological systems or normal chemical systems to do types of reactions, which are often under constant temperature and constant pressure conditions. And so again, we define a new type of energy, and this, we call it the Gibbs energy, and it was because it was formulated by Willard Gibbs, Yale, and he did so much seminal work in thermodynamics that, quite a few things, Gibbs phase rule, other things are named after him. It's defined this way. Oftentimes your book and quite others will recognize that we already define this as the enthalpy. So oftentimes you'll see it just written as H minus Ts. But just to write it out in its full form, I would write it as fundamental variables, that it's U plus PV minus Ts. So we can look at that. We can think of it as a double Legendre transform on both PV and TS from our internal energy. We can look at it. We can look at the change in the Gibbs free energy related to this, that it could be the change in the enthalpy minus the temperature, the change in the entropy, if we're at constant temperature, right? In other words, if you can go through this. So you often see this. In fact, one of the fundamental equations you see is that DH is, or DG is DH minus TDS, right? Or written more like, oftentimes like this. Now that assumed when you were doing a derivative through this term here that temperature was constant. And oftentimes, it's almost always formally stated in textbooks, but often we're always just looking at lists of equations. And it's one of the things I like to emphasize, really make sure when you're looking at different equations, students will say, God, there's so many equations for the same thing, for enthalpy or for Gibbs free energy or entropy. It's oftentimes, just like before when we saw the entropy, for reversible systems, it's this. For irreversible, it's this. It's often knowing when you write an equation that you write what the assumptions are, that this is at constant temperature. Become very important in when you can use certain ones, et cetera. And this I specifically write because of its incredible importance in biochemistry and life processes, et cetera. So while the second law tells us that we maximize entropy, we're going to minimize our energy, and specifically our Gibbs free energy, and we're usually doing this at constant temperature and pressure. And your book kind of goes through the systematics of this, and then it goes directly into some very important processes in biochemistry and biological life processes, like, for example, the ordering of water around hydrophobic molecules, or this hydrophobic interaction, and how you can kind of understand that based on some things we already talked about how entropy looks at the amount of order disorder and how you can order these water molecules around hydrophobic things, and how that helps us understand at a microscopic level how you can decrease entropy, or how entropy type changes balance each other. Okay, and then finally, it talks about it in the way when we talk about constant temperature and pressure, that about just chemical work, that when you're at constant temperature and pressure, and so the mechanical term drops away, and so does the heat term, and you can look at it as just the extra work or the available work in a chemical process for chemistry, or for things to change, number of moles to change based on their chemical potentials and interactions. And very importantly is, just like we can define spontaneity, how we came back in the very first of this chapter to look at spontaneity and its relation to maximizing entropy, spontaneity in these constant temperature pressure processes minimizes this Gibbs free energy. And so if the Gibbs free energy ends up getting less than zero, it's a spontaneous process. Greater than zero, the change in Gibbs free energy is a not spontaneous process, et cetera. And so it's very important that we make that relationship back to entropy. So, and then like I mentioned, the book then, it's very critical after you've kind of looked at some of these concepts and grappled with them yourself, that you really look through the key concepts, make sure you understand them. I list the key equations here, a lot of which we covered in looking at this overview, because it's really the mathematical definitions that really give us our biggest insight into this. And then it's critically. In fact, hopefully we'll have time to make some videos on discussion questions, and then go through really doing this builds and solidifies your understanding of these concepts. And the key concepts is doing some of the exercises and projects associated with this. I hope this overview helped on the second law, and it'll be followed up with future videos on each chapter within this text. Thank you.